Welcome back to OCR MEI Further Mathematics B. Today we're doing chapter 3.7, Vector Line Equations. When it comes to vector lines, it's kind of similar to how vector planes work, except the equations are slightly different. We've talked about how the vector plane can be thought as a particular position vector projected along two direction vectors, but for a single line, rather than having two different directions that you can project, you're limited to only projecting in a certain direction. And so you have a directional vector with a coefficient added onto a certain dot on the line. That would give you the vector. Similarly, there are Cartesian equivalents of it, which is given as below. It's not a beautiful equation since it's not some x plus some y plus some z equals to some constant, but you just have to bear in mind that this is this define a line vector. The vector form is way more used than the Cartesian form, unlike the vector planes. So this is one thing that you need to bear in mind. And it's important to know that the two lines in 3D can have three different formations. They can either intersect, they can be parallel to each other, and they can be skew from each other, where the skew form is way more abundant than either intersection or parallel. And for this video, I'm just gonna briefly talk about the geometry of the lines. I'm not gonna actually go into any calculations because it gets out of hand quite fast, and I want to do it next video when we actually have some purpose of calculating certain relations between lines. You will not be asked to fabricate certain line vectors, but if you need to find 2 points, if you're given 2 points and you were to join the two position together, normally you have point vector A and you have point vector B. To find the displacement, you take the difference between these two vectors. This is the normal case, and this would result in the directional vector D. And so what you would do to find the entire line, if you project infinitely, basically either side go as far as you can, you should get either r equals to a add lambda d, where d is defined as a take b, or r equals to b plus mu d, where mu is a different constant to lambda. These two will be equivalent, and if you know the coordinate of A and coordinate of B, then you should be able to solve for lambda and mu for a particular unit direction. So that said, we can now look at the geometry of lines. So let's say I have L equals to C plus sigma R. Why not? And I'm gonna swap this B away to a G, vector G. Okay, so we now have three vectors. I need to rename this as, let's say, K. So I've got three vectors, R, K, and L. The obvious thing to check for is to check for the direction. So for the line vector R and line vector K, they have the same direction vector, which means that they have to be parallel or the same or equivalent. So if G is exactly A, or if G lies within R, then they had to be parallel. And if G equals A, then they are the same. So the thing that you need to bear in mind is that being the same is not the same as being parallel, although parallel is a larger set than being the same. Being the same has to mean that every single component equals. So G has to be A, D has to be D, which was defined as true. Mu has to be lambda, then K is equal or the same as R. There's also one that is basically just they overlap, they are parallel, but they are not the same. You can state that as either overlap or just parallel would work for this particular formation. Now I've covered the same directional vector formats. Let's look at R and L instead this time. We've got A and C. We've got lambda, sigma, which means that they should normally not be the same. We've got two directional vectors D and R that are not the same. So since D and R are not the same, they cannot be parallel, which means that they had to be either skewed or have a solution, or I have to write have a solution. So as we have learned, having a solution means that they cross each other. But in 3D space, that is often very difficult to formulate. If they share a dot or a point, which means that A is equal to C, or you can kind of shift around. Basically, if A is a combination of C plus n lots of R, where n can be arbitrarily anything, then you have two lines that crosses each other, which means that they have a solution. In numerical form, it's easier to try to solve simultaneous equations to equate vector R with vector L and try to solve for lambda and sigma with given D, A, C, and R. So you have two equations, you have two variables, and you should be able to calculate said solution. but often it's going to be skewed, which geometrically looks a bit weird and it's difficult to describe. Let's try this out. So imagine a line. This is just a line, except the thicker end is closer to you, because doing 2D things, doing 3D things on 2D is difficult. So basically I've got essentially this is exaggerated with the line closest being this way, furthest being this way, vice versa. If I do the normal description, it's gonna look like a parallel line. So this is the form, this is the actual form that you're looking at. This is exaggerated so that you know which way is which. They are perpendicular to each other, which is kind of obvious over here, not obvious over here. You can do this in the real world by taking two pencils or pens, put them parallel on each other, and find a spot, then start to twist the two pencils. Then you should be able to get a skewed formation, except they are touching, so that you need to separate them perpendicular to how the point along the point that you have skewed the two pencils. So if you did that, then you should be able to see the 3D geometry, and yeah, this skewed form will come in handy next video when I talk about calculating the actual shortest separation between a skewed two skewed pairs of lines. With that said, however, this will be the end of this video. There isn't much to ask as of this time, and yeah, basically if you have any questions regarding vectors, do leave a comment in the comment section below, and I will see you on my next one.